Thank you for the introduction, Sasha. And then also I'd like to thank all the organizers, especially the Professor Alexander, for his heroic effort to make this happen. And also it's my great pleasure to see the friend whom I have not met for a while due to COVID-19. So the title of my talk has been changed. So I'm going to discuss evidence for quantum critical charge delocalization in the unconventional superconductor serum rhodium 5. So if you have any question, then please stop me in the middle so that we can talk. Okay, so most of the talk, the work that I present today has been performed by my postdoctor, Dr. Wang, and then student Tuson Park. And the samples were provided by partially Eric from Los Alamos National Lab.
Recording in progress.
Okay, so hold a minute. So the outline of this course is after a brief introduction to functional quantum matter, and I will discuss how to control connectivity by tuning the AFM quantum critical point. And then lastly, I will present evidence for quantum critical charge delocalization in unconventional superconductor, serum rhodium 5. Okay, so recently, new materials and platforms with exceptional novel functionality has been reported. To name a few, the superconductivity at room temperature has been reported in hydrogen-based superconductors. And I think I needed to remove the, this one, okay. So then the strongly correlated state has been also revealed in twisted bilayer system at a magic angle around 1.05, and the via Kunda semi-metal and multiple quantum critical point has been also reported. Even though the phenomena are very rich, there are fundamental the blocks that make these interesting phenomena happen. For example, conduction electron, and then spin, and the lattice vibration phonon, and the orbital degree of freedom, especially the orbital and the F orbital. So understanding how these building blocks interplay with each other to promote these exceptional functionality is a very important issue to realize and to control the node functionality in quantum matter by maximizing those quantum effects. The quantum critical matter has served as a seabed, a rich avenue for promoting node functionality. For example, when you control when you tune the control parameter, the ordered phase, for example, here we show antiferromagnetism, is suppressed to 0 Kelvin, we call it a critical point. And then with further increasing the control parameter, then we reach quantum disordered state. And because at this critical point, all the competing interactions are degenerate, that the quantum critical matter appears. Some of the features in the quantum critical matter is the so-called stranded metallic behavior and the non-formula liquid behavior. And then in the quantum disordered state, that the small Fermi surface changes to larger Fermi surface, and flat band often appears. Experimentally, unconventional superconductivity has been also observed in the vicinity of the critical point. Like in the high-density plate, dome of superconductivity appears in the vicinity of the magnetic critical point, and also iron-based nuclide also shows these nice dome, both electron doping and hole doping, and also the helium compound under high pressure that they also shows superconductivity. However, the presence of the current critical point beneath the superconducting dome is still an issue, and also the precise relationship among magnetic order, non-permitted behavior, and unconventional superconductivity are still controversial. The serum rhodium-indium-5, the subject compound that I will discuss, is the ideal system to address those issues. Serum rhodium-indium-5 forms in a tetragonal structure with serum-indium planes stacked along the C-axis. And then this is the three-dimensional phase diagram, temperature, pressure, and then magnetic field. Where the dome of superconductivity appears when this antiferromagnetic state is suppressed, and then the strange metallic phase appears in the normal state. This is a two-dimensional temperature pressure phase diagram, and as you'll feel that at pressures lower than 1.7 GPa, then superconductivity and magnetism coexist together. On the other hand, at higher pressure, only superconductivity arises. When a magnetic field is applied, then inside the superconducting dome, then there is thermodynamic phase transition to antiferromagnetic state is revealed, and this line exists well inside the superconducting dome, showing revealing the presence of critical point. And at this antiferromagnetic critical point, the quantum oscillations measurement shows that at this point, F electrons changes from localized to itinerant. So, and also correspondingly, the Hall coefficient shows the divergence at this magnetic critical point, showing that the serum rhodium-indium-5 has a quantum breakdown type critical point, where the not only at magnetic transition temperature go to zero, also so-called the quantum destruction in its scale is the local or the charge delocalization and its scale, and at AFM critical point. So this is the temperature and then control parameter phase diagram by Wu and Tremblay, based on 2D periodic Anderson model with frustrated hybridization. Here, V is on-site hybridization, and V5 is nearest neighbor hybridization. So when you change the ratio between the on-site and the nearest neighbor hybridization strengths, then you can change the magnetic antiferromagnetic critical point, and then superconductivity arising from these critical fluctuations, they move together with AFM to CP, providing a way to tune the superconductivity by controlling the AFM to CP point. Well, to summarize, I mean, this approach, well, we can usually see superconductivity arise in the vicinity of AFM to CP. So what does the theory predict is that if you move the critical point to another point, right, then there may be a case when superconductivity, well, does not move at all, meaning that the superconductivity, well, does not arise because of a QCP. It's just purely accidental. However, if they move together, then it's a very strong argument that spin-activity arises because of the concrictor point. So we tested this simple scenario on the binary compound chromium arsenide, which becomes superconducting under pressure. And then this is the resistivity control plot together with the phase diagram. And here, the AFM QCP occurs around, well, like around 8 kilobar. And then dome of spin-activity is around here, like centered around 9, 10 GPa. 10 kilo. So it's pretty close, and making very plausible that they may be related. So what we did was that we wanted to move around the AFM QCP and see if indeed spin-activity is connected with it or not. So when we did aluminum doping to chromium arsenide, this is what we found was that the QCP moves from 8 kilobar to 4 kilobar. Right? You can clearly see a phase transition from AFM to paramagnetism. Yet the dome of spin-activity did not change much, which means that even though if you do not see this one, then you may argue that spin-activity arises from the concrictor point. But by performing this, the experiment, we can clearly say that spin-activity is accidentally located in the vicinity of QCP in chromium arsenide. How about in heavy fermion compound, the silicon media file? So we show that the concrictor point is hidden inside the dome of spin-activity around 2.35 GPa, right? At the point where this strange metallic behavior occurs in the normal state. So what we did was that we did a thin doping and then moved the T-now, right? So then what we found was that the critical point moves from 2.5 to 1.4, right? Not only the AFM QCP moved, but also dome of spin-activity moved together with it, clearly showing that spin-activity and critical point is intrinsically connected, which provide a rare example of spin-activity realized by this so-called Kondo breakdown. Okay, so then so if this is a Kondo breakdown type of a concrictor point, then I think we expect that they should be accompanied by the Fermi surface change from small to large. Because of these, the Kondo destruction energy scale or charge delocalization point, which has not been observed yet. So this is 4.4% serum rhodymedium 5, the control plot of magnetic resistivity, where the total resistivity is subtracted by the phonon part. And then, so you can see that, I mean, here, hold on. This antiferromagnetic phase boundary, right, nicely extrapolated to around 1.3 or 1.4 GPa. Then dome of spin-activity occurs at around this AFM QCP point. However, the magnetic resistivity, the enhanced magnetic resistivity does not end here, but rather, like it has the anomalous behavior, well within the antiferromagnetic state, suggesting that well, there may not be just one critical point, maybe two critical points. Okay, so in order to address this issue, that we have performed experiment both pure compound and the 4.4% tin-doped selenodium 5 compound. The resistivity and hole measurement, and for selenodium 5, because we need higher pressure, we use the diamond angle pressure cell and measured it up to 60 GPa. And the 4.4% tin-doped compound, we did use piston cylinder type pressure cell of 3 GPa. Okay, so here we show the magnetic resistivity under pressure, in plane, and then you can see that at a high temperature, in the high temperature, the magnetic resistivity increases because of the quantum scattering. And then there are three characteristic temperatures, around 50 Kelvin, the broad maximum, which we ascribe to the due to the crystal field splitting, and then the hump around 8 Kelvin, we ascribe to the coherence of the double ground state, and the T-nail around, I think it's 2.7 Kelvin, 2.4 Kelvin. And then with the increasing pressure, that the resistivity increases because of the enhanced hybridization. And you can see the overall. And then in the higher pressure, you can see that still the resistivity increases due to enhanced hybridization. However, at lower temperature, that the resistivity start to decrease at pressures above 1 GPa or 10 kPa. So this is the color contour plot of electrical resistivity, and you can see that a strong enhancement around 0.9 GPa, so we call it PC1. However, the exponent of the resistivity, which is stated by rho is rho per ATS of n, is most prominent at the AFM QSP line around 0.3 or 0.4 GPa. Okay, so we see two different critical points. And then when you use the formula liquid T-square dependent analysis, we also see two features. One, the residual resistivity has a maximum around PC1, while the A coefficient, which is proportional to the effective mass, diverges at AFM QSP. Okay, so what is this critical point 1, right? We know, PC2 is AFM QCP. So in order to understand it, we did a whole measurement for this compound. And this is data at ambient pressure. And at high pressure, at high temperature, that the temperature dependence can be well explained by the two terms, namely the normal term and the skew scattering term. And when you estimated it, it explains pretty well. But at temperature below 50 Kelvin, it diverges, suggesting there is additional source of contribution to the whole coefficient. And here, the minimum or the amplitude is actually maximum, but the minimum we call the pseudogate temperature, which in case of selenodium 5, it was ascribed to pseudogate temperature. So we call it that way too. And then we can see that the pseudogate temperature in the tin-doped is almost independent of the magnetic field strength. So here we show the low temperature Hall coefficient for several pressures. With increasing pressure, the pseudogate temperature decreases and the signature becomes weaker, and around 1 GPa is gone. And at higher pressure region, we can see that the local minimum occurs again. But we think that this is not due to pseudo gap, so we call it just T sub L, right, indicating something is going on. And this is the whole coefficient for pure similarly unified compound, and at temperature below the AFM2CP point, you can see that pseudo gap temperature and then decrease with increasing pressure. And pressure is higher than critical point, then you can see that additional point, the new types of minima occurs other than in the high pressure region, which is similar to the 4.4% in the compound. Okay, so this is the contour plot of the whole resistance in the temperature and pressure plane. Then you can see that the maximum in the whole resistivity occurs at near the AFM2CP point, and then the pseudo gap temperature, and also this new line, right, that shows the local minimum also, and at this critical point. So how about the 4.4% kindle compound? Okay, so this is a QCP point, and pseudo gap is pretty much, I think, and here, on the other hand, this T sub L, new temperature scale, okay, and here, where the whole coefficient is maximum, okay, and you can see that the whole coefficient has a peak, but continuously change across this critical point at the QCP point. Okay, so meaning supporting that there is additional critical point PC1. So how to understand this new temperature scale T sub L and the new critical point PC1 in the Kindle? So according to this scenario, the quantum breakdown type, then this quantum destruction or charge delocalization point should end at this point, right? So we can think that this point actually represent this charge delocalization point. So that also in Tyndall compound, this is a SPW critical point where this is star local, and within the antiferromagnetic phase, which is what happens here, and leading to an anomaly in the whole effect, and then a resistivity. So we can conjecture that the separation or the appearance of a new critical point inside a phase may be due to a transformation of quantum breakdown type QCP in pure compound to a spin density wave type QCP by thin substitution. So then the question is, how that is it possible, right? We just do thin doping, only 4.4%, but in minimal doping. Why it happens? So this global phase diagram by Chimiao et al. Provides some hint. But this is x-axis quantum coupling, y-axis the frustration parameter. That if it's a cubic compound, then the fluctuation of the local moment is small. So that's why, when you tune J, then you go from antiferromagnetic small to antiferromagnetic large, and then the paramagnetic space with large formation space. On the other hand, in the more two-dimensional trio, the fluctuation becomes large, and it actually go from antiferromagnetic small to antiferromagnetic, then paramagnetic large formation space. So we can naively, I think we can think that like ytterbium rhodium silicon 2, which is the candidate for quantum breakdown quantum point, that pure compound track from here, this number 2 line from F small to permanently large quantum space. On the other hand, when you dope with cobalt to ytterbium rhodium silicon 2, when you dope, if you dope tin to rhodium 5, then it becomes more less frustrating, or the degree of quantum fluctuations of the local cerium 4F local moment is smaller. That's why it has to go through the AF small, the AF large, and then the paramagnetic large formation space going through this path. And the superconductivity, I think I have maybe 3 minutes or so I'm going to briefly wrap up my talk. And then here, the superconductivity in the cerium rhodium 5, well, this is a very rare example of conductor critical point, right? Where we suspected that not only spin but also charge degree of freedom, they are involved in producing superconductivity. So, however, the tin doped compound clearly shows that the spins are involved in producing conductivity, not the charge degree of freedom. So this one rule out the scenario that charge fluctuation or valence fluctuation, I think, suggests that we can rule out the scenario.
Recording stopped.
So, okay, so then, but it clearly shows, suggested that magnetic fluctuations are tied to AFM QCP mediate the formation of group of pairs. Okay, so to summarize the talk, that we successfully moved the AFM QCP from 2.35 to 1.35 GPa, and then showed that superconductivity moves together with it. Okay, and then we discovered the new temperature scale named T star L, signifying the transformation from a small to large formation phase, both in cerium rhodium 5 and then the tin doped compound. And then here, in tin doped compound, we showed that the delocalization critical point actually end deep in the AFM phase. With that, I'd like to thank you for your listening.